You want that down? OK. This is our generator coroutines, really the answer. My name is James Powell. We're at PyData London 2024. It is Friday, June 14th, 2024. So if you see this talk 10 years from now and you're like, wow, none of that actually applies to anything that we do anymore, well, now you know why. Let's get started. Let's take a look. Now, before we get started, a lot of you, when probably reading through the abstract, didn't really know what it was talking about. So I want to start with just some very basic terminology. I know the proposal said that there was no prior knowledge needed. And so I'll see if I can run you through at least the main parts of the prior knowledge. Specifically, the terminology. Well, it turns out that unfortunately, the terminology around things like generator and generator coroutines is quite confusing for no really good reason. But we'll start off with something very simple. This is what we call a Python function. This is what we call a function. This is what the Python interpreter calls a function. This is what the documentation calls a function. And some people, if you're old enough, might even call it a subroutine. You can look at the function itself. You can invoke the function. There's really nothing too fancy. Now, this here is what people call a generator. And when you call that thing, you get a generator instance. But that's not what the Python interpreter calls a generator. Python interpreter says this is also a function. It's just a function that returns a generator. And so we already see an immediate break in the terminology. Don't ask me why they made it so complicated, because if we dig into this structure here, we'll see that as a GI underscore frame. What does GI stand for other than generator instance? For some reason, they call the generator instance a generator, but it still has a GI underscore frame attribute on it. I don't know why they had to make it so complicated, but it gets a little bit worse than that. It turns out that this thing that we're looking at here is actually a function that returns a generator. And we could say that, you know what, that terminology really only appears in maybe the interpreter internals when we actually look at the thing itself. Or if we look at the collections.abc module and ask if something's a callable or a generator, it might say, oh, no, that's actually the function, what is returned as a generator. But it gets a little bit more complicated than that. Now, people might say this thing here with these set of protocols, iter, next, send, throw, and close, is what we might call the generator or the generator-coroutine protocols, and the implementation of those gives us a generator. And the collections.abc module agrees with you. It says anything that has these 5 protocols is considered to be a generator because it's largely equivalent with something that's formulated like this, and thus from the outside we really can't tell the difference. You know, duck typing is a big thing in Python. However, I don't know that we'd really call that a generator. It's debatable, and oftentimes when people describe things like the intertools module, they say it's full of generators. Well, much of the intertools module is really written in C, so it's not really clear if it really is a generator, or the generator is the thing in Python with the def and the yield in it. I don't know. But it gets a little bit worse than that beyond that. Because, well, before we even get to that, here, this is what we might call just these 2 parts as an iterator, and people already get confused with what an iterator is, distinct from an iterable. An iterator is just something that implements iter and next, which is distinct from the iterable, which just implements iter. Oftentimes, you'll see in examples of this, when people are trying to explain it, they'll combine these into one entity, which is wrong, because the distinction between the iterable and the iterator is actually a very important one. The iterable is the state itself, sorry, the iterable is the data itself, and the iterator is the state for that data. But here's where it starts to get a little bit ugly. For those of you who've been using Python for a while, this is what we would call a coroutine, because we would say, from a computer science perspective, it is a generalization of a subroutine, where a subroutine has input once and output once. This thing can take multiple inputs and give you multiple outputs, except the Python interpreter does not distinguish this thing from a regular generator. So this Python interpreter will say this is a function that returns a generator, and the word coroutine won't show up anywhere inside the interpreter internals or really in the documentation. And where it gets even worse than that is, nowadays, if you look through the Python documentation, you'll see people call things with an async def a coroutine. The collections.abc module, the capital C coroutine, the collections.abc module is referring to this thing here. And so probably most of you in attendance at this talk right now came because you were interested in asynchronous functions, and we're not even going to talk about those at all. Because this is what they call a coroutine these days, but it's not what we used to call a coroutine back in the day, and it's not what we're actually here to talk about. I apologize, the terminology is so confusing. I may be trying to make it a little bit more confusing for you, but it frustrates me that we have all of these terms and that we reuse them in some ways. But the really fun part of it is, with the async def syntax that was added in Python 3.6, we can actually put a yield inside an async def. And so if you really think about this, if we were to make use of the thing that this yield gives us back, this is what we could call a capital C coroutine, a collections.abc coroutine, lower C coroutine. We could call this thing a coroutine squared if we so desired. But we're not really here to talk about asynchronous tasks. We're here to talk about generators and the extension of generators, that is, generators where we take some additional partial input and then use it to model something. So let's talk a little bit of background. What is the generator itself? Well, fundamentally, a generator is really our means by which we can take some computation and break it down into parts. We can decompose it, and then that decomposition can be used to accomplish some goal. In the case of the async syntax that was added to Python, that goal there is interleaving operations in order to waste as little time as we can waiting for things. But the actual use case of a generator-coroutine is quite broad. In fact, this is one of the parts of the Python language that I am continuously surprised is not actually used by anybody. I'll be reading through like the PyTorch documentation, and you'll see something and it says num epochs to train some model, and be like, this should have been a generator. How is it that you people who are very good at writing Python cannot seem to understand that there are these basic features that we have that we should be using instead of these extraordinarily clumsy approaches that you see with like num epochs or different ending modalities of a computation. But before we get into that, let me show you what I mean by decomposing a computation. So here's a little bit of dummy code, and there's only maybe one or two interesting things about the dummy code. The first thing is this is a representation of maybe some data pipeline, and so the data pipeline operates on entities, what we might call datum, the singular of data, which means that if we had a base class for it, it would be a datum base. So our data base would contain multiple datum objects whose base class is datum base. I found that very humorous when I was putting this together at 3 a.m. in the morning. But if we actually fast forward to the part that really matters here, well, the part that really matters here is we have some operations like loading some data, removing some outliers, normalizing data, analyzing data, and we have something that looks like this, the operation of our report itself. And when we look at that, we say, this is one computation. It does a bunch of stuff and it gives us some output, but it can actually be decomposed into individual parts. And that decomposition is something which many of us can squint at and come to different decisions on where that decomposition is. For example, some of you will look at this and say, well, doing a report, well, there's actually 4 steps here. You load the data, then you clean the data, and then you process the data, and then you print the data. And other of you will say, oh, there's actually 6 steps here, because each one of these lines of code represents one step, and we can't really say that removing the outliers and normalizing the data is step 1A and step 1B. And we can debate this back and forth as we so desire, because it turns out for a typical Python function, the decomposition of that into parts is ambiguous. And so, as a consequence, the Python interpreter really has 2 options for what it can do with this. Either 1, it can run this thing to completion. This is what we call eager computation. Or 2, it can run this bytecode by bytecode, which, if you think about it, that's how threading works in a global interpreter lock world. But what we can do with the generator is we can delineate the parts of the computation, and we can do that in a way which eliminates the ambiguity. We can put yield statements in between, or we can put yield keywords, I should say, in between each of the steps, and then it is unambiguous where one step ends and the next step begins. And as a consequence of this decomposition, we can do something interesting. For example, we can run the parts of the computation we want to run and not run the parts of the computation we don't want to run, which is why, for example, anytime you see some computation and it's got a bunch of keyword arguments that indicate where the ending modalities are, run this computation for a set number of steps, like a solver. Run this computation until it meets some threshold condition, like a backtester. Run this thing until you see some environmental state generated, like some kind of state machine or agent model. Well, that can be modeled as a generator or as a generator-coroutine, where the modalities for how you stop the computation are now externalized. Rather than you having to specify them in keyword arguments, they're controlled by the end user, which adds an enormous amount of flexibility to their use of your tools and also significantly, substantially simplifies the APIs. I'll show you an example of this, one that really surprises me that these things still are out there to this day. But with that said, I can show you one more time what it means to decompose some sort of computation into parts. Here we have a function. It has 4 parts, step 0 up to step 3. And all we can do with this is run it to completion. However, if we were to delineate this into 4 steps, we can run the steps we want, and in the middle, we can go and do whatever we want to do in the middle. We can go off and do some arbitrary operation in the middle, and we can do something else here. Ooh, let's make sure we comment that back. And we can run only the parts we choose to run. This is oftentimes what is referred to as lazy versus eager computation. And for those of you who have heard of that and have some thought that maybe lazy computation has some benefit to your work. I want to show you how that fits into our notion of what a generator is. Well, if we think about it, when we talk about something like a generator, this decomposed computation, we can really time two sorts of things in it. We can time what historically I've called the incremental action and the decision point, but what you could also call is just the incremental computation, the step that you've broken it down to, one individual step, and the mechanism by which you advance this. And if you were to time those, and you can represent these in various ways, we can look at this in the for loop functionality where you can think that the advancement of that is really just stepping through that for loop, so it's the next call that's happening behind the scenes when you decompose the for loop into the while true formulation. Well, if you think about it, there's kind of like levels and edges, and you're timing the levels and edges. You're timing how long it takes to get into the generator, and then the time that's actually spent in the generator, and then you go out of the generator, and then you come back in. Well, we could draw out two ends of a spectrum. On one end of the spectrum, the time to do work is quite fast. Incremental operations are very, very fast, like on the order of a nanosecond. And the time to advance, or the time to decide, is relatively slow, like 1 microsecond, which, between you and me, is just about the approximate speed of running one Python bytecode. One of the assumptions that we have here is that the generator-coroutine formulation is something that we can only really access from the pure Python layer. It's not something that we could embed into a restricted computation domain. On the other end of the spectrum, however, we have cases where the work is relatively slow, like 1 millisecond. And the time to advance this thing is about still 1 microsecond, because it's about 1 Python bytecode. And if you think about the two extremes here, you can understand why it is that eager computation and lazy computation, why we don't see things like generators in a lot of data science code. If we're on the end where the work is really fast, the incremental work is really fast, and advancing through a Python mechanism or making a decision for whether to keep going is relatively slow, then our best bet is do a bunch of extra speculative work and throw it away. Because with these timings, you could do 1,000 units of additional work before it takes time to do 1 Python bytecode to actually advance to a generator. This is why when you look at things like pandas and NumPy, they tend to be eager computational tools. However, on the other end of that spectrum, you're looking at units of work that are relatively large, which is why ideally what we would see in any libraries that make use of NumPy or pandas, but not NumPy or pandas themselves, anything that sits upon that where the actual unit of work is, for example, training a machine learning model or performing some complicated multi-stage arithmetic expression where the unit of work is relatively slow, well, it makes sense for us to have greater control over how we advance through that, and this is where we want generators. Well, the reason why we don't see generators, at least in the core tools, is the unit of work is relatively small, and the reason we don't see generators in some of the larger formulations that we have, the machine learning model, the training formulations, the data pipelines, is data scientists aren't very good Python programmers. Now, I'm sorry, but it's the truth. I'm sorry, it's the truth. Now, if we think about the spectrum from, say, subroutines to generator-coroutines, well, that's fairly straightforward. Here we have a function or a subroutine. You can imagine that it takes input at one point in its operation. It runs through every single step, and then it gives you all of its output all at once. When you think about a generator, what happens is you give it some input, and then you incrementally get the incremental outputs, and you can decide how many of those you want. So if this is infinite, you can actually get something useful by terminating this early. Obviously, an infinite sequence of data is not something that we can practically use because, as far as I can tell, the world in which I live is finite. For a generator-coroutine, the only distinction here is we're actually making use of the ability to send data back into this. So what we can think is a computation is really the inputs and the outputs that determine it, and a generator-coroutine is really just taking that one computation, breaking it down into parts, and then allowing yourself to send small inputs in and get other inputs out. And you have one large running computation. This is what a generator-coroutine. Now, there's one thing that probably some of you didn't really notice when we looked at the very first decomposition where we took the load data, clean data, report data, which is that's something that likely would not actually be done in practice. If we take, as an aside, a little bit of our terminology around homogeneity and heterogeneity, one thing that we can see that's kind of interesting is if we're decomposing a computation into parts, we could say that that decomposition is a heterogeneous computation, like this, where cleaning the data set is a very, very different operation. If you're removing outliers or normalizing the data set, then loading the data set, these are very different operations. They'll have different inputs, they'll have different outputs, and they'll behave in different ways. And so it's unlikely that we might decompose it in this fashion because if you're going to work through this thing manually and you do a next, you don't know what that next does. Does it clean the data set? Does it report? It would be completely unusable. On the other hand, typically where we tend to see generators in practical use is when we have these decompositions that are largely homogeneous computations. So for example, some large for loop, and every step is basically equivalent to every other step. If we think about it, there's really different ways that we can operate with these things. We can do some sort of automated processing through or automated advancement through or operation through the generator coroutine, through the computation, like with a for loop or like with an event loop of some sort. or some manual operation. And again, it is unlikely that that manual operation would ever coexist with a heterogeneous computation because you'd never know what is that next actually doing. But if it's homogeneous, what is that next actually doing? Well, whatever the last next was doing. This is why we oftentimes don't see the reformulation of the implicit state machine that you'll see in an object-oriented model into a generator coroutine because it's far too heterogeneous. However, this actually leads to a very interesting correspondence because if we think about our homogeneity and heterogeneity, the terminology, and as we actually apply it in Python, we typically in Python don't talk about strict homogeneity and strict heterogeneity. We talk about this in a looser sense. For example, if we happen to have a list in Python that has 3 integers in it, we would say this is strictly homogeneous. That's what we typically think about when we think of homogeneity. But in Python, we actually say, you know what? If it's got 3 numbers in it, an integer, a float, and a complex number, this is loosely homogeneous. Yeah, it's strictly heterogeneous, but we can treat it as though it's homogeneous. It's good enough. And if we happen to have, say, 2 numbers and a string, we might say, well, this is probably heterogeneous. What can we do to a numeric value and a string value inside a body of a for loop in any consistent fashion? However, it actually turns out that when you start talking about the looseness of homogeneity and heterogeneity, it really becomes a very subjective thing because from the perspective of this code, you actually can do something. From the perspective of this code that just prints these values out, this is homogeneous. It's loosely homogeneous, except from the practical perspective of how you'd actually use this. Like, what can you actually do to a string value that you can do to a numeric value? Almost nothing. So you really have to look at a very degenerate use case to find, or to subjectively view this as homogeneous. Now, a really interesting aside, because I've been thinking about pandas quite a bit, and the last time I spoke about generators and generator coroutines, I talked about this in terms of building simulation frameworks, specifically portfolio rebalancing frameworks. And one of the interesting things that came up at that presentation was the idea that in pandas, the data frame is not really a very well-founded entity, but the series actually is. And so I did want to spend an enormous amount of time putting together a lot of code to show you an example that I thought was quite interesting when it comes to the idea of the subjectivity of heterogeneity. Because it turns out that when we are modeling something like, let's see if we can model this thing, when we're modeling something like a set of trades, let's see if we can get this thing to work. Well, it turns out that, okay, we'll run this way. It turns out that the typical modeling for, say, a trading framework is one in which we are going to, it's one in which we're going to assume that, say, the things that we trade, let's see if we can get this. Oh, I think we actually have a, okay, let's see. We have to get our little auto runner to run again. So that's our problem. So when we're dealing with trades, it's often the case that the modeling that we typically have is one where we'll have like a data frame, and one column will be the amount of the entity trade, and the other column will be the cash that we traded hands with. And we'll view this as some kind of homogeneous set where we have 2 different columns. But that's actually not a very well-founded view, because if you think about how a trade might actually work, a trade might have multiple, shall we say, legs to it, where, for example, you can't necessarily trade in the currency or in the units that you want. And let's see if we can get this. We're having a little bit of difficulty getting our auto runner to work. But we'll see if we can get that going, and if we can't, then we'll proceed through this differently. And let's see if we can get this example to go, otherwise we're going to be in a little bit of trouble. But typically, the formulation that we have is one where it's one where very, very unfortunate. Well, we'll have to go without that. So it's basically one where the modeling has 2 columns. One column is the entity that we traded, and the other column is the cash that we traded. But a better modeling of this is a series modeling, where we actually have only one column of data, and that one column of data is both the cash that traded hands and the volume. And what the stack and unstack operations actually are in pandas are a way for us to toggle between 2 subjective modes of homogeneity. It's a little bit of a stretch, but we'll move on just for the sake of time. Well, one thing that we might think about when we're thinking about how we use generators in practice and how we want to write code in practice is the idea of iteration helpers. And iteration helpers come up quite a bit. We'll see even in the built-ins, even in the Python standard library, we happen to have this focus on things like iteration helpers. For example, if in pure Python, what we wanted to do is we wanted to process some raw CSV data, we might discover that the code that we have here on the screen is erroneous because there's a header line in that CSV data, and when we try to compute a numeric value from that header line right here, it's going to blow up in our face. And so we might say, how do we deal with that header line? And the worst answer that we can have is to add a lot of loop administration. We can say line number equals 0, and if line number is equal to 0, then skip that line and then increment the loop number. And this ends up making our loop body extremely noisy. Well, unfortunately, it also has a risk of hiding certain bugs, because if we forget to increment this line number here, we might discover that the code actually works, but it doesn't process any data. And so we end up with code that's not particularly satisfactory, even though it's fairly easy for us to write. The idea of an iteration helper is for us to identify that in the code that we are writing, one of the things that leads to the readability of our code is the clarity of our loops. Specifically, that the loop header tells you exactly what the loop is going to do, and the loop body is minimized down to just the lines of code that represent the work that you want to do, minimizing the amount of administrative trivia that's happening in that loop. And so this is why we might choose to use something like the built-in enumerate, because in the built-in enumerate, we no longer have that tracking of that line number, we no longer have that risk of that bug, and we have code where that loop header tells you exactly what you're going to do. You're going to look at the names and the values and the line number, and then in the body, you choose what you do with that line number. You say, if it happens to be the header line, skip it. Now, we can oftentimes extend this idea in directions that are not particularly valuable. And this is actually where iteration helpers and writing good iteration helpers can be somewhat difficult. Because you might say, why don't I further remove some of the mechanism from this loop? Specifically, what I'm going to do is I'm going to write a skip headers that just skips all of my headers. And I'm going to make the decision for you. And thus, my loop becomes just one line of code doing the data assignment here. And you might say, well, I still need to leave that code in the body of the loop, because who knows what kind of additional ad hoc data transformations I might want to do there. You know, maybe I want to multiply this value or take the absolute value here, and I don't want to encode that in some modality somewhere, because ultimately there's not going to be any sufficient intentional repetition here for me to be able to do that. However, it turns out that that formulation for an iteration helper is not particularly good, because it robs us of actually doing anything with the modality. In practice, when we want to write iteration helpers, what we want to do is we want to reveal data to the person who's doing the iteration in order to give them greater ability to decide what to do in the iteration. So rather than skipping headers, what you actually probably want to do is marking headers, so that in the body of the loop you can decide what to do, in this case skip it, or if you decide that the header determination is wrong, you can miss it. And this is one big problem that I see anytime you talk to a data scientist who's writing some code. They try and shove all the functionality into some kind of functional element, and they end up robbing the end user of the flexibility of choosing to do different things, like, oh, maybe I don't want to skip the headers, or maybe what I want to do is actually want to take the header data and use it in order to, for example, support arbitrary column ordering. Whatever the case may be, the writing of iteration helpers tends to be something that we need to apply a little bit of care to doing correctly. Well, here's another example of iteration helpers, and a very common one. Let's say we have some data and we want to do some sort of quarter-on-quarter report. And here's how we might do it. In the naive approach, we have a previous date and a previous value, and then we're looping, and there's a lot of noise in this loop. We're managing what the previous date is. We're setting it again at the end, and this is not particularly satisfactory. It's very hard to read, and it's really crowding out the actual logic of what we're trying to do here, which is just print out the report. And there may be alternate ways for us to write it. For example, this is a little bit less noisy, but you can see that there's a lot of risk for an off-by-one error, because we have to compute the indices and we have to intermediate through these indices. And if we do the -1 in the wrong place and we loop from 0 up to the size of this thing, we get into trouble. So we have to make sure that we loop from the first index, so this -1 doesn't have an index error, or erroneously it won't have an index error. It'll actually give you a negative index. So you could be comparing the first month against the last month. And so you'll have all sorts of weird errors here. The better approach that we might take is, and what makes this even worse is when somebody comes to us and they want to extend this report in some fashion. For example, they want to print out something different on the first line and something different on the last line. Then we end up with a bunch of code, some sitting inside the body of loops, some sitting above the loop, some sitting at the bottom of the loop. This code's not even right, because if there are no entities for us to iterate over, we run into trouble. We try and actually access entities that don't exist. Or if there only happens to be one entity, we end up duplicating 2 of our rows. So what can we do? Well, this is another case where we can write an iteration helper. Use of the iter_tools module comes up all the time when we're talking about iteration helpers and we're talking about generators, because these are small building blocks that we can use to build up better iteration. And this is why we choose to take these approaches in pure Python. Here, the use of pairwise significantly reduces the amount of noise in this loop. isolates all of the behavior to the header, and you can see exactly from that header exactly what you're doing. You're looking at previous dates and current dates in order to do some sort of comparison. And of course, if you're a pandas user, this is basically a pandas.shift, pandas.diff type operation. This is what we might call value disintermediation. One thing that we see often in scientific user code is they oftentimes are too fixated on the mechanics of the code in which they're writing, and so there'll be a lot of intermediation through indices, which, by the way, is actually the approach you take in NumPy or pandas. I'll talk about that in a moment, but you oftentimes see people doing things like for index in range len whatever, and you as a Python programmer say, no, just for x in whatever. We don't need that extra intermediation, it's unnecessary. And this is the general pattern that we're seeing here. Well, this is because in Python, our general approach, in contemporary Python at least, is to disintermediate values and to operate almost solely on rich objects that are floating around our system, and then to take incremental high-fidelity objects and stick them into a restricted computation domain. It happens to be the case, however, that in the restricted computation domain of the NumPy and D array and the pandas data frame, the pandas series, one of the things that we can't embed into that is, for example, calling arbitrary Python functions, because we don't really have a way to embed that into the restricted computation domain. And so as a consequence, we still do need that index-style intermediation. For example, if you have some pandas data frame and you want to do some sort of maximization on an alternate predicate, in pure Python you do a sorted with a key function, but in pandas you'd have to do an index max, or in NumPy you'd have to do like an argmax, and then take the result of that and then feed that back into it. And so this is probably why a lot of these scientific users end up writing code like this. But it's our goal to say, you know what, let's just directly operate on the entities we have, directly operate on the pairwise of these things. When we take a look at good Python code, one of the things that we see, at least contemporarily, is that we have this value disintermediation. And a larger view of this value disintermediation, as represented by this motivating example, which we'll come back to later, which is actually a fairly good motivating example if you think about how well it analogizes to things like strategy systems, backtesters, portfolio, rebalancers, is the idea that the naive way in which to represent maybe some card game that players are playing, where they have different strategies, you want to see which strategy wins. Again, very analogous to some kind of agent model or some kind of backtesting mechanism, is there's lots of dictionaries all over the place. They have strings in them, and people are associating these strings over here with these strings over here, and there's a lot of if-else stuff. And the modern style, or at least the contemporary style of Python, is skip all of that nonsense and operate directly on entities. Operate entities like generator-coroutines representing the strategies themselves. You don't have a string representing the strategy, actually represented as a live, rich entity that the garbage collector can maintain as it sees fit. Operate on richer objects like enum.enum, packaged up into data classes.dataclass or named tuple, and cycle over these items directly, interact with these items directly, let the garbage collector decide what the lifetime of these things are, and since these entities will typically be relatively few in number and fairly high level, this will all work out fairly well, as long as, of course, when you have your high fidelity, your high granularity objects of high number, you stick them into a restricted computation domain. Now, returning to our motivating example, well, what you can see here is the use of iteration helpers is a significant benefit to this code, because even if you include things like do some operation first and do some operation last in this looping, well, we can just add another iteration helper like an is first, is last, based off of nwise, which I'm sure many of you have seen before. And one nice consequence of this is we get all of the functionality of this loop inside the loop itself. We have the first action, the first line that you print, all the middle lines, and the last line, all in the loop itself. Now, where we tend to see generator coroutines in practice is in any sort of arbitrary modeling of a state machine. Because if you think about like a state machine like this, there's probably 3 different ways we can formally represent some kind of state machine. The first way is implicitly in some object-oriented formulation where nobody can tell what needs to be called in what order. You've all experienced this before. You're working with some object, you call some method, it blows up in your face, and somebody says, no, you have to call this method over here first. You can't call that one because there's a sequencing. And then somebody says, oh, I'll go into my init, and their init will be variable A, variable B, variable C, variable D equals none, 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 to try to initialize everything in order to bypass the sequencing. But the sequencing is implicit in the model itself. This is almost impossible for anybody to reason about, almost impossible for anybody to read. The other approach that they might take is the canonical approach, where we represent the transitions and the states independently, and then we write some executor for that. And so here, this is a very standard modeling of something like this. You know, we have state A goes to state B or state C based off some predicate, and then our executor determines how we transition through this state machine. And it's a fairly simplistic modeling, but the problem with this is we have something akin to retained mode UI. Anytime I see some vendor show me, here's my data pipeline or my data platform, and they say, oh, you have sources, and you have sinks, and you have these callbacks you can send in, I say, no, please, I don't want that. Because understand that for my use case, I'm measured on time to market and research velocity. And the way in which I manage that is by minimizing the variance. If something takes an hour for me to do, that's okay as long as I can maintain that variance of it'll take an hour, not an hour or a day. And the way in which I retain that control over the variance of the outcomes of the work that I do is by retaining control over what I have. So I don't want it to be the case that I have to model some state machine or some state graph here specifying the sources and the sinks and the connectivity and then pass it along to somebody else's event loop, because at the point where I decide that I need, or I discover that I need arbitrary control flow or arbitrary data flow, I have to wait for that vendor to come back to me and say, oh, here's version 2.0 with the little call point, the hook point that you needed. That's a terrible lifestyle. I don't want to go back to my stakeholders and say, oh, you wanted to pass data between these two nodes of our data pipeline, but I can't do it yet. Version 2.0 is coming out next week, and that has that functionality. It's a terrible lifestyle for everybody, and it blows up the variance of delivering anything. And so what I might want to do instead is I might want to represent this as a generator-coroutine. But do note that even if I'm not that worried about that extra, or to put a point on that, understand if we took this particular state graph and we need to add some additional data flow, specifically that you transition from node D back to node A only if some other data, like you've only transitioned through node C a certain number of times, you end up having to rewrite all the transitions. You end up having to rewrite the whole executor. It's extremely noisy and extremely messy. So when you're working with those kind of vendors, what happens is they release version 2.0. Good news, I can do what I want to do, but I have to rewrite all the code I already wrote. Or they have some clumsy mechanism by which everything is loosey-goosey, and there's like keyword arguments all over the place, and nothing is strict enough to prevent me from doing something wrong, and then I'm fighting the tool because I can't actually figure out what it wants from me. The alternate approach is to take something that's akin to maybe an immediate mode UI approach, where I model this as a generator-coroutine. And in the generator-coroutine formulation, I'm actually modeling the state graph, and I control the state machine. So I have something that looks like this. And here, I can add in arbitrary control flow and arbitrary data flow as I see fit. One very interesting thing here is we can see that a generator-coroutine actually ends up linearizing the state graph in something that looks like a function. So I can reason about this very well. There's an infinite loop. That infinite loop goes from state A to state B or state C. That's just an if-else. Then to state D, and then back around to state A. I can see this here, which I couldn't see on the canonical modeling using the transitions. And if I needed some arbitrary additional ad hoc behavior, such as we transition from state D back to state A based on some condition, it's just a local variable that I have to add. Generator-coroutines add an enormous amount of flexibility whenever I'm modeling these kind of state graphs because I control the event loop, which means I control the data flow and I control the control flow as I see fit, which means the variance of my work effort is minimized because if a stakeholder comes to me and asks for something very, very much different than what I had expected this to look like, well, I can just go in and add a couple of local variables and a couple if-else branches, a while true or something like that, and I'm off to the races. I don't have to rely on whoever provided the event loop to do that for me. Any of you who've worked with PyQt or any of those frameworks, you know there's a million callbacks all over the place, and you have to figure out exactly the right ones at exactly the right place. This is honestly still a problem with React. I don't understand why they didn't switch React to an immediate mode UI, but whatever, that's the case. Now, do note that these things are actually useful. So, one of the problems that we have when we look at, say, scientific computing code, things like scipy.optimize.newton, is oftentimes when these things are written, you'll see these like additional keyword arguments, like scipy.optimize.newton has like a max iter and an rtol and whatnot, and it just becomes very complex, and the users, the authors of these have to determine for me up front what modalities for completing this are. Any backtest or any simulator, any agent model, any state machine really should be modeled instead as an infinite sequence of states, and then externally I control what states I want to look at. And if you look at SciPy, if you look at some of those tools, many of which predate the introduction of generators into Python in their defense, you'll see that we have these gaps here where the APIs are significantly harder to test, significantly more complex than what we need. Trust me, if you are training machine learning models and you have some code that says train it for this number of epochs, and you pass that in, and then somebody says, well, actually, can we train it for fewer epochs, so train it until some threshold is met, and you add another keyword argument, you're going in the wrong direction. The problem is, and the question that arises when we ask ourselves, are generator-coroutines really the answer is, unfortunately, we cannot send a non-none value to a just-started generator. This is a consequence of the design and how the Python interpreter actually operates on these. We have to retrieve a value by doing a next and then send a value afterwards. And as a consequence, this forces us to observe a first rest modality. In other words, because we can't send a non-none value to a just-started generator-coroutine, the thing that we do first on it and every other subsequent action look different. The first operation has to be a raw next, and all the subsequent ones can be .send. And this first rest modality has a significant problem that arises because compositionally, if we have multiple first rest modalities, well, we can't actually tell if we're at the first or not. Because if you think about it, what will happen is, if we have to observe, or we have to do something different on the first thing and then the rest, and then we chain two of these things together, what happens? Well, the first modality appears arbitrarily in the middle of the chained operation, and there's no way that you can tell that it's going to be there. One of the solutions that we typically have for this that tends to add a lot of conceptual complexity for a lot of users is pumping or priming. And in pumping or priming, what we do is we add a dummy yield so that we can advance past that first modality. But what we're not doing is eliminating the modality. In fact, we're trading this modality. We're taking a first rest modality and turning it into a rest last modality, where only the last step is distinct from the rest. However, in practice, this tends to work out because if these things are infinite, then that last modality is not really observable because it's the end of an infinite sequence. But ultimately, because there's a strict linear sequencing of the operations here, you have to do input and output one before the other, there's always going to be some modality. There's always going to be some distinction between the very first action and the very last action. Pumping is not generally a solution to this. It does not eliminate that modality. And do note, critically, pumping is not the answer in every case because in many use cases, for example, playing a card game, sometimes when you're playing a card game, the first player plays a different card to the table because there's no other card that they're going to play against. They do a distinct action. There are many use cases where the first action is distinct from all subsequent actions. Now, the compositional use case gets very, very messy. And if we dig into, say, how yield from PEP380 delegation to a subgenerator works, we'll see that pumping is actually something that's built into the Python interpreter, but the compositional problem becomes really messy because we can't really chain these things very nicely together. We have to go through multiple distinct iterations of how we chain this to actually get it to work. And I'll fast forward to the formulation that actually works. The unfortunate thing is much of the itertools module isn't really written for generator coroutines, and if it's the case that we want to do simple compositional actions on sequences of computations, take this computation to do this computation next, we end up having to degrade all of our code back to its original formulation. Let me show you what the correct formulation of a chained operation looks like. You can't even use PEP380 yield from on this thing. You have to actually break it down into the while true so you can actually make sure that you're piping the last input into the next step. I don't want to write a while true try except. That's what PEP380 is for. This is what all these tools are for. And yet, unfortunately, one consequence of the way in which the itertools module is designed and this pumping or priming problem is oftentimes we're using generator coroutines. We end up having to reconstitute much of these common libraries, and then we end up having to drop ourselves back down to this while true formulation, which again is extremely clumsy. In fact, in practice, because almost nothing in the itertools module actually supports generator coroutines, we probably, if we want to use them, need to rewrite at minimum chain, drop while, filter false, islice, take while, and zip longest, and we can litigate whether the other ones are actually useful. It's kind of, it's unclear to me whether combinations actually make sense in the case of a computation that you're breaking into parts. Now, another important consideration, one of our last considerations is we can't pump a coroutine squared very easily as a consequence of needing knowledge of the event loop in order to provide the pumping. So none of these three options here actually effectively pump this generator coroutine. None of these will work. In fact, in order to pump a generator coroutine, an asynchronous generator coroutine, we actually need to either distinguish between a pumped and an unpumped generator coroutine by injecting the await syntax into this using just a regular decorator, which is the style that we like to use for just a regular generator coroutine, or we have to wrap this whole thing in an enormous amount of extra code, and it's extremely noisy and messy. Unfortunately, asynchronous code, by virtue of needing knowledge of that event loop, makes the pumping and priming problem very problematic in practice. And in fact, I don't know that there's a better answer than this for pumping a coroutine squared. Now, I know many of you are very concerned about this problem of pumping coroutine squared, but trust me, it's actually something that is quite problematic. Now, finally, when we talk about our value disintermediation problem, a lot of things come up that start getting a little bit ugly. Here, this is the final example. I wish I could show you this working code, but in this final example, I show you an example where we're playing the game of Uno, which is a very interesting modeling of a generator coroutine. Because you think when you play the game of Uno, there's like a skip card and a reverse card, and the ordering changes. Like when you play a reverse card, you go reverse through the ordering of those. And you might think, how do I actually model that? And naively, and originally when I was starting to work with generator coroutines, my thought was, well, the ordering in a game of Uno is a state machine, where you're injecting into that long-running computation the card that was played, like a skip card or reverse card, and that's affecting the ordering. When you play a reverse card, the players go in reverse order. When you play a skip card, you skip over a player. But it turns out that this is very poorly generalizing, and it's really hard to test. Instead, you have to actually re-intermediate yourself by doing things like writing basic generators or paired generators that operate on the same state, like a bidirectional ordering, in order to actually make this work. And in fact, it turns out that in practice, many cases where you might think that a problem could actually be modeled by a state machine and logically appears that it should be, it's actually much better to model this as just a regular generator, maybe even a paired generators that operate on some consistent state, in order to retain the testability and the generality that you want. In practice, it turns out that working with generator coroutines is actually quite difficult. When you work with generator coroutines, you need to have a very keen eye on the design of the code that you write, and you need to be very careful about, one, pumping and ordering and sequencing, because that first rest modality and the last rest modality is something that is very, very easy to get wrong, and it's very easy to go in circles. Additionally, you have to be very careful about trying to avoid writing generator coroutines and instead writing just simple generators in most cases, because unfortunately, when you write these generator coroutines, they oftentimes over-specialize on the business entities that you have, which then makes them less testable. And so the final version of the UNO example that I had for you here is one where there's a lot of mechanism, but one where you can see some of the benefits of the generator coroutine. Here, we have some strategy that we can extend later. One of the things that we didn't talk about so much is API unification, where you make a generator coroutine look like a callable, look like a class. So you give your end users the ability to represent or to model like a strategy in any way. They write a class, they want to write a class, they want to write a closure, they write a closure, they want to write a generator coroutine, they can. And where we model the game loop as a composition of these entities, the initial dealing, the pile, the player's action for playing, and we compose them with our PEP380 yield from. This seems to mostly work and lead to code that is relatively reasonable, relatively readable. We instantiate a game. We loop through that game forever until we no longer have a game. Although you can see it's kind of unfortunate. In order to get that return value, we actually have to do the try except inside the while true. We yield out all of the actions of the game so we can record the exact state of the game, who drew a card, who played a card, and whatnot. But it still remains to be seen. Are generator coroutines really the answer? I'm not certain, because a lot of the cognitive overhead that's here does draw to question whether the benefits of this linearized modeling is really there. There's a lot of additional work that we have to do. We need to prepare ourselves and prepare quite a bit of our code as well as our helper libraries in order to be able to work with these entities. And in exchange for that, what do we get? Well, we get a much more testable, much more readable, linearized view of a state machine that is maybe more extensible, maybe more flexible, hopefully more readable, but as I've seen it play out in practice, sometimes it works and sometimes it isn't, and I'm not quite sure what the dividing line is between what works and isn't. This has been our generator coroutines, really the answer. I'm James Powell. Thank you very much.